In this video, I will talk about Riemann sums and how we can use Riemann sums to approximate area under a curve. So basically we are looking at areas like this one. So if this is f of x, this is a, some number a, and this is some number b. So we want to approximate this area. And from our other video, we know that this area will be the value of the definite integral from a to b of f of x. So first, let's look at this example. Here we want to look at area under the graph of f of x equals 3x squared minus x plus 1 over this interval, interval 4, 7, using three rectangles. So when we are given interval like that, we mean from x equals 4 to x equals 7. So the first step when working this type of problems is to try to draw the graph of the given function. So let's do that quickly. We know that this is a parabola. If you want accurate graph, you can use some graphing calculator or some online graphing tools. But here we'll just try to graph it approximately. We are interested in the region between 4 and 7. So I'm going to locate 4 somewhere here and put 7 somewhere over here. So when x is 4, the y value is, let's say we can simply figure that out by plugging in 4 for x. That comes out to be 3 times 4 squared minus 4 plus 1, which is 45. 3 times 16 minus 4 plus 1 comes out to be 45. And similarly, you can plug in 7 to figure out f of 7. So 3 times 7 squared minus 7 plus 1, which will give us 141. So at x equals 4, we have 45. We are at 45. So I'm going to suppose this is at 45. So this point here. And at x equals 7, we are at 141. So I'm going to assume this is 141. So the graph goes like this, from that point to that point, and sort of parabola. I can extend a little bit on both sides. So let's suppose this is the graph of function given function f. So we are interested in finding area under this graph from x equals 4 to x equals 7. So this area, and the problem says using three rectangles. So we want to divide this, the interval from 4 to 7 into three equal rectangles. So we can do that by taking 1 unit for one rectangle, width of 1 unit for one rectangle. So we can do 5, 6, and 7. And this part, here we are using left endpoints. So at each sub-interval, we are going to use left endpoint. So at this interval, we will use 4. So we will draw the height of the rectangle at 4. So our rectangle will look like this one. And in the next interval, again, left endpoint would be 5. So we will draw height of the rectangle at 5 up to the curve, like that. And the last rectangle in this one, again, the left endpoint is 6. So draw height of the rectangle at 6 up to the curve. So now we need to find area of these three rectangles. So for that, we need to find the length and width of each rectangle. The width for each rectangle is 1 here, 1 here, and 1 here. So you see from 4 to 5 is 1, 5 to 6 is 1, 6 to 7 is 1. So all these values are 1. These widths are 1. And we need to find height. The heights may be different. The height at 4, the first rectangle, is given by this length. this length. And you see the y value at 4 is 45. So this length must be 45. So for the first rectangle, area is 1 times 45. Now let's move on to the second rectangle. The width is still 1. We need to find height. The height of the second rectangle will be this one. And looks like this height will be simply f of 5. So for that, we need to evaluate f of 5. F of 5 will be 3 times 5 squared minus 5 plus 1, which comes out to be 3 times 25 is 75, minus 5 is 70 plus 1, which is 71. So the height for the second rectangle is 71, because that point is 571. And similarly for the third rectangle, we need to get that point, and the y value at that point will give us the height. So for that, we simply need to find f of 6. So f of 6 is going to be 3 times 6 squared minus 6 plus 1. What does that come out to be? So 3 times 6 squared is 36. 3 times 36 is 108. Minus 6 is 102 plus 1. So this will come out to be 103. So that will be the height of the third rectangle. Now we just need to add these three. So we have, I'm going to use my calculator. We have 45 plus 71 plus 103. So that gives us 219. So using three rectangles, the area is approximately 219 using left endpoints. Now let's repeat the process using the right endpoints. I'm going to try to draw the graph again. Our 4 is here and 7 is here. So it goes through the point 4, 45. And through the point 7, 141. So this is how the graph looks like. Just copying that part. Again, we want to divide into 3 parts so that we can find the area between 4 and 7 approximately. So dividing into 3 rectangles, one would be from 4 to 5, another would be from 5 to 6, and 6 to 7. So 4 to 5, 5 to 6, and 6 to 7. The only difference is that we are looking at the right endpoints. So in this interval, we are looking at this point at 5. So we draw a rectangle with height at 5. So it will look like this one, the first rectangle. For the second interval, again, we look at the right endpoint, which is 6. So draw a rectangle with height at 6 up to the graph. The same thing with the third interval. Draw a rectangle with height at 7 up to the graph. So we are looking at area of these 3 rectangles. So to find the area, we just need to calculate, to approximate the area under the curve, we just need to calculate area of these 3 rectangles. For the first rectangle, width definitely is 1. The height would be this length, which is the y value at 5, and we already found that over here. So that is 71 plus, for the second rectangle, again the width is 1 times the height of this rectangle. We found that to be 103 over here. And in the third rectangle, we again have width 1, this width, and height is given by this length, and that we know is 141. So this will give us the area, approximate area under the curve. So we just need to add these three and you will get 315. So 315 is the approximate area under the curve using three rectangles and right endpoints. Just by looking at the graph, if you look at the first one, here we are leaving out some parts. So for example, we are leaving out this part here, that part here, and this part here. So the area we got by using the rectangles is going to be underestimate. And for the second one, we are adding in some extra area, these three parts. So this will be overestimate of the actual area under the curve. Okay, next we have the same function and same interval, but this time we are using 6 rectangles instead of 3. Again, let's start by drawing the graph of the function. We already know how it looks like. And we have some values also. We said at 4, it goes at 45. So 445 is a point on the curve. And at 7, it goes through 141. 141 is a point on the curve. So we can approximately draw the graph like that. And now this time we want to divide this into 6 equal intervals. So between 4 and 7, when we divide into 6 equal intervals, so let's first divide into 3 intervals. So 4 to 5, 5 to 6, and 6 to 7. So we have 3 equal intervals. Now we can divide each interval, each sub-interval into 2 parts so that we get 6 intervals. So I'm going to divide this into 2 parts so that this will be 4.5. This one will be 5.5 and this one will be 6.5. So now we want to draw rectangles, 6 rectangles using these 6 sub-intervals, and look at the left endpoints in the first part. So our first interval is this one from 4 to 4.5 and our left endpoint is 4. So I'm going to draw a rectangle at 4 so that the height goes up to the curve. The second rectangle will be at 4.5 to 5 and the left point at this sub-interval is 4.5. So we draw a rectangle with height at 4.5. So it will look like that one. The next interval is 5 to 5.5. So we can draw a rectangle with height at 5 because 5 is the left endpoint in this subinterval. Next we draw at 5.5. At this interval, this is the left endpoint. On the interval 6 to 6.5, 6 is the left point. So we can draw at 6. And in this interval, 6.5 is the left endpoint. So we can draw at 6.5. So this is what we got. So we need to find the area of these 6 rectangles and add them up. That will give us approximate area under the curve. So for the first subinterval, the width is this length here from 4 to 4.5, and that is definitely 0.5 times height will be given by this length. So this is the y value at 4, which we found to be 45, plus, now onto the second rectangle, the width is 0.5 again. They all have the same widths, all these rectangles. And to get the height, we need y value at 4.5. So we need this value, this length, so which is the y value at 4.5. So because this point is 4.5, f of 4.5, we need to find f of 4.5. So plug in 4.5 in the function. So basically you want to do f of 4.5 in the function, which is 3 times 4.5 squared minus 4.5 plus 1, which comes out to be 57.25. 57.25. So that is the height for the second rectangle, 57.25. Plus, for the next rectangle, we again have width 0.5 times the height will be the y value at 5. And we know that point is 5. We calculated that in our previous example, and we got that to be 71. So 571. So the height of the third rectangle is 71 plus, now for the fourth rectangle, the width is still 0.5. For this rectangle, width is still 0.5 and height will be the y value at 5.5. So we need to find this point. And to get that point, we just need to evaluate, we just need to plug in 5.5 to the function, and that will give us 3 times 5.5 squared minus 5.5 plus 1, which will be 86.25. 86.25. 86.25. So this is the fourth rectangle. Now the fifth one, the width is still 0.5 for this one. And for the height, we just need to find y value at 6. So this point here, I'm going to write that up here. 6. And we found that in our previous example, we found that to be 103. So the height of this rectangle, the fifth rectangle, is 103. And finally, for the last rectangle, we have again width 0.5 times height is given by this length, which is the y value at 6.5. So we just need to find that point. So this point is 6.5. Again, plug x equals to 6.5 in the function, and that comes out to be 121.25. 121.25. So now we just need to multiply these and then add them up. So for that, I'm going to use my calculator. So this comes out to be 241.875. This comes out to be 241.875. So this is an estimate of the area under the curve using 6 rectangles. Now let's try the right endpoints using right endpoints. So I'm going to quickly try to draw the graph of this function. Basically copy the graph over. We know at 4, the y value is 45. And at 7, y value is 141. So this point. So the graph should look like that, like we have here. Now again, we want to divide into 6 sub-intervals. We want to divide the interval 4, 7 into 6 sub-intervals, just like we did in this example. So first we can divide into 3 sub-intervals, 4, 5, 6, 7, and then divide each into 2 parts. So the first one, 4.5, 5.5, and 6.5. Now, in each of these sub-intervals, we want to look at the right endpoints and draw rectangles with height at the right endpoints. So for the first sub-interval, the right endpoint is 4.5. So we want to draw height at 4.5. Like this. So draw a rectangle with height at 4.5 up to the curve. For the second sub-interval, we want to look at, again, the right endpoint, which is 5. Draw a rectangle at 5. It will look like that. For the third sub-interval, draw at 5.5. For the Next one, fourth one, 6 is the right endpoint. For the next one, 6.5 is the right endpoint. And for the next one, 7 is the right endpoint. So we have these rectangles. So now we need to find area of each of these rectangles and add them up. Beginning with the first rectangle, the width is 0.5 and the height is this length here, which is the y value at 4.5. And we found that to be 57.25 over here. So we can just use that times 57.25 because we found this point to be 4.5, 57.25. So the height of the first rectangle is 57.25. Similarly, for the second rectangle, we have width 0.5 again, and the height is the y value at 5, and that we know is 71. Plus, for the third rectangle, again, we have width 0.5, and the height is the y value at 5.5, this length, and we know that is 86.25. For the fourth rectangle, the width is again 0.5 for this rectangle, and height is we are looking at the height at 6. So this height, so that we know is 103. For the fifth one, width is still 0.5, and the height we are looking at the y value at 6.5, which we know is 121.25 plus the last rectangle, 0.5 times this height, which is the y value at 7, which is 141. So now we just need to add these and we'll multiply 0.5 with each of these and then add them up. So for that, I'm going to use my calculator. This gives me 289.875. So this is an estimate of the area under the curve using right endpoints. Now looking at the rectangles and the graph, you see in the first case, we left out some areas like these parts we left out in the first case. So the value we got will be underestimate of the actual area under the curve. And in the second case, we picked up some extra areas like these ones. So those are not under the curve, but they are included in 289.875. So this will be overestimate. So the basic idea behind Riemann sums is to divide region into several rectangles and add up the area of the rectangles. So let's quickly go through the process. Let's say we are looking at this function f and we are looking at area from A to B. We are trying to estimate or find this area. So first we want to partition the interval AB into n subintervals. So n can be any number. So we have a bunch of partitions here. We will denote A by x0 and the last value by xn. So if n is 5, then B would be x5, for example. And then this one will be x1, x2, and so on. So somewhere over here, you will have xi. The next one will be xi plus 1, and so on all the way up to xn. And then if we do the partition such that all the subintervals have the same width, then each of the interval has width b minus a over n, because we are dividing the length b minus a into n parts. So the width will be b minus a over n. And we select ci to be any point in the interval. So in the interval, in the ith interval. So if we look at this interval here, so this x value is Ci. That x value over here, we call that to be Ci. For example, your C1 would be over here, C2 would be over here, and so on. And the last one, Cn, would be over here. The nth value, Cn, would be over there. So in the ith interval, we want to find area of the rectangle. We are drawing the height at I. So this rectangle will look like this one. The width is simply delta x, which we know is b minus a over n. And the height will be given by this length. So since we know this point is going to be Ci f of Ci, the y value is f of Ci. So the area of this rectangle is b minus a over n times f of Ci. So we have a formula for each of these rectangles. These are all these tiny rectangles. So all we need to do is just add them up to get the area of everything. So like it says here, then the area of the whole region can be approximated as the sum of these tiny areas. To get the exact area, we want to make n very large. So making n very large means allowing n to be infinitely large. That means we just need to look at the limit as n goes to infinity. That will give us the exact area. Now, depending on what type of endpoints you want to use, we can find formula for Ci. So for example, if we are looking at this region from A to B of under function f, so this is the ith interval. And Ci, if you look at the right endpoints, the Ci will consider that to be here. This is one possibility, and the value of Ci will be given by this formula, A plus I delta x. If you look at the left endpoint, Ci will be over here. In that case, we have this formula for Ci. And if you're looking at the midpoints, Ci will be given by this formula. So if you look at midpoint in its interval, so consider that to be Ci. So we have these three possibilities. Some people like to look at some other possibilities. So these are not the only options, but these are quite standard ones. Okay, let's look at this example. So they want us to find the integral, definite integral 4 to 6 x squared using the limit definition. Area equals limit n goes to infinity of this expression. So we want to first evaluate this expression, then find the limit. First, let's try to draw the graph of what we are trying to figure out. The problem wants us to find the definite integral of x squared from 4 to 6. X squared, the function x squared looks like this one. So this is f of x equals x squared, and we are looking at the region from 4 to 6. So we want to find this area, because this area will give us the integral from 4 to 6 of x squared dx. And it wants us to use this formula. Let's start by copying the formula down. We have limit n goes to infinity, b minus a over n, sum I equals 1 to n f of Ci. And we are going to let Ci equals a plus I delta x. Now let's plug in the values we know. We know what a and b are, so we can find delta x also. This will look like limit n goes to infinity. B minus a will be 6 minus 4 over n. Summation I equals 1 to n, and f of ci. So f of ci. So we'll first figure out what ci looks like and then plug that in here. So ci is, here we are using the right endpoints. So we have the formula ci equals a plus I delta x from our previous slide. So a is 4 plus I times delta x is b minus, so delta x, let me put that formula here. Delta x is b minus a by n. So our b is 6, 6 minus 4 by n. So this will look like 4 plus 2i over n, 4 plus 2i over n. Then we are looking at f of 4 plus 2i over n in this expression. Now this becomes limit n goes to infinity, 2 over n, sum I equals 1 to n. And we know f of x is x squared. So f of 4 plus 2i over n is 4 plus 2i over n squared. Let's try to evaluate this expression in the parentheses first. I'm keeping everything else as it is. So when we square this, you can basically write 2 copies of 4 plus 2i by n and FOIL. So you get 16 plus 2 times 4 times 2 is 16i over n plus 4i squared over n squared. So we get this. Now I can apply this summation to each of the terms. I'm going to draw a line here so that we have more space to write. So this becomes limit n goes to infinity, 2 by n times sum I equals 1 to n of 16 plus sum I equals 1 to n of 16i over n, but 16 over n is independent of I, so I can just pull that out of the summation. So 16 by n over there. So sum of I plus the same thing with the last expression. So I can pull out 4 by n squared. Then we are left with sum is sum of I squared. Okay. So now we have a bunch of sums to evaluate. 2 by n. The first one is sum I equals 1 through n of 16. So basically we are adding 16n times. So we get 16n plus, next we have 16 by n. And sum I, we can apply this formula over here. So that will be n plus 2 by 2 plus the next one 4 by n squared. So we have sum I squared, we can apply that formula. So n plus 1 times 2n plus 1 over 6. Okay, let's multiply each of these terms by 2 by n and also simplify as far as we can so that we can do the limit. Limit n goes to infinity. The first expression becomes 32, just 32, plus the second expression becomes 16 on the top, n times n plus 2 divide by, well, we have this 2 by n also. So I'm going to put that 2 over here. Okay, plus 2 by n times that. So this 2n over here plus 2 by n times 4 by n squared, n plus 1. I could actually write all of this as one fraction. n plus 1 to n plus 1. And then in the denominator, we actually have 6n squared. 6n squared. Now, the last step here is to try to simplify this expression and do the limit. So I'm going to erase some of this stuff on the top so that we can have some place to write on. So okay, this should be good enough. So we have a limit n goes to infinity. The first part over there is just 32 plus. The second part, we have 2 by n. So on the top, we get 32. But I could actually cancel out 2 from top and bottom, remove that. So basically, I can cancel these 2 out with that. So we just have 16 times n squared plus 2n. If I distribute n, divide by n squared, plus, next we have, I can cancel out this 2 and 6 divide top and bottom by 2. That will give me 3 over here. So that comes out to be 4n. And I can also actually cancel out this n with that n. So we get 4 over 3n squared. And over here we get n plus 1 to n plus 1 over 3n squared. So let's simplify one step further. So that will give us limit n goes to infinity. 32 plus 16 n squared over 32 n over n squared plus, so this will come out to be, looks like 8 n squared. When you multiply 4 times n times 2n plus, so I'm just going to fold, 4 times n times 1 is 4n plus 4 times 1 times 2n is 8n plus 1 times 1 is 1 divided by 3n squared. Okay. Finally, we can do the limit. As n goes to infinity, 32 is 32 plus, as n goes to infinity, since we have n squared and n squared on the top and in the denominator, we can just consider the coefficients. So 16 over 1 will be the second limit. Plus, as n goes to infinity, we have 8 over 3 as the third limit. So this is the area. Now we just need to add these 3 terms. 32 is 96 over 3 plus 16 is 48 over 3, and then we have 8 over 3. So we can now just add these 3 fractions and we get 152 over 3. So this is the area under the curve. This area, and which is the value of this integral. Here is next example. Here we want to evaluate the integral of the function 4 plus 3x squared from -3 to 1 using the same definition, the summation definition. So let's begin by drawing the graph of this function. So we're looking at values from -3 to 1. So let's suppose x equals -3 is here and 1 is here. And we can quickly figure out some of the points so that we can have the graph. When x is 0, y would be 4. So let's suppose 4 is somewhere over there. When x is 1, y is 7. So it should go through this point. If we say this is 7. When x is -3, y would be 4 plus 3 times -3 square, which is 9. So 4 plus 27. That will give us 31. So if I say 31 is over here, so we are looking at the graph going through that point. So let's approximately draw the graph. It's a nice parabola going through these points, like that one. And we're looking at the area under this curve from here to over here. So we're trying to figure out this area. And this area will be the value of the integral, -3 to 1 of this function, 4 plus 3x squared. So we start by writing out the formula. Limit n goes to infinity, b minus a by n, sum I equals 1 to n, f of ci is the formula we have for area, where ci, we can again use the right endpoints like in the last example. So a plus I delta x. And we know a is 3 and b is 4. So this is our a. I mean, b is 1. B is 1. This is our b. So it will look like -3 plus I. And delta x is b minus a by n. So delta x will come out to be b minus a, 1 minus -3 by n, which is 4 by n. So I'll have 4 by n. So 4i by n. Delta x is 4 by n. So we have f of, we have ci. Now we can use that in this formula. So b minus a by n is 4 by n. Sum I equals 1 to n, and f of ci will be, for now, I'm just going to write that as -3 plus 4i by n. This becomes limit n goes to infinity, 4 by n. Sum I equals n. F of x is 4 plus 3x squared. So f of -3 plus 4i by n is going to be 4 plus 3 times whatever we have here squared. So that is squared. This becomes limit n goes to infinity, 4 by n. I equals 1 to n. So we need to simplify this part. 4 plus 3 times, so when you square this part, you should get 9, because -3 squared is 9, plus 2 times -3 times 4i by n will be -24. So -24 I by n plus 4i by n squared, 16 I squared by n squared. Next, let's simplify this one step further. So this becomes limit n goes to infinity, 4 by n. Sum I equals 1 to n. We have 4 plus 3 times 9 is 27 minus we have 3 times 24 is 72 I by n, plus we have 3 times 16, which is 48 by n squared I squared. So now we can distribute the summation to each of the terms. So we get limit n goes to infinity, 4 by n. Then we have sum I equals 1 to n of 4 plus sum I equals 1 to n. Actually, we could combine 4 and 27. I just saw that. So 4 plus 27 is 31. I'm going to put 31 over there. Plus, next one, we have a negative 72 by ni. Since 72 by n is independent of I can pull that out of the summation. So I can write that as 72 by n I over here. And next we have 48 by n squared times summation of I squared. We have this. So now we just need to use these formulas and find these sums. Let me free up some space over here on the top. I'm going to start writing over here now. So this becomes limit n goes to infinity, 4 by n in the front. Then we have sum of 31 n times, so 31n minus 72 by n is over there, and sum I is n plus 2 by 2 using this formula. n plus 2 by 2 plus 48 by n squared. And we have sum I squared, which we have over here, the formula for sum I squared. So that will be n plus 1 to n plus 1 over 6. I can actually simplify a few things here. Looks like I can cancel out n and n. And if I divide 72 by 2, I should get 36. And I can also cancel out this n, and I'll get n over here. And 48 by 6 is simply 8. So let's write down what we are left with. And in the meantime, we can distribute this 4 by n also. So this becomes limit n goes to infinity. So 4 by n times 31 will simply be 4 times 31 because n's will get canceled out. So this will be 124 minus, so 36 times 4 by n will be 36 times 4 is 144. Then we have 144 by n plus 2 plus, now 4 times 8 is 32. 32 over, then we have n times n, which is n squared. And on the top, we have n plus 1 to n plus 1. Now let's simplify these wherever we can so that we can do the limit. So 124 minus, we have 144n plus 288 by n plus, we have 32 times n times 2n would be 64. n squared. Next we have 32n, 32 times n times 1, which is 32n. Next we have 32 times 1 times 2n, which is 64n. Next we have 32 times 1 times 1, which is 32. So this all divided by n squared. Now we are ready to do the limit. As n goes to infinity, 124 is 124 minus, as n goes to infinity, for this one, since we have order 1 polynomial of order 1 on the top and in the denominator, so we just need to look at the coefficients of the leading terms. So 144 over 1 as n goes to infinity. And over here, the same thing. We have both the quadratic functions on the top and in the denominator. We just need to look at the leading term, the coefficients of the leading terms. So we get 124 minus 144 plus 64. That comes out to be 44. So it comes out to be 44, and this is the value of the integral. So I can say this is 44.